So now let's get to the point of best fit line. So let's again go ahead and draw the graph where we had x and we had y, and given some points, we wanted to find the best fit line. So what we were doing, we were starting to plot for a given intercept. We were plotting different lines and seeing which line would fit, or which line would actually fit all the points in the data the best out of all. So we started moving from this to this, and in the path we realized that this has this much distance, this another point has this much distance, this another point this much distance, and so on for different points, right? So then we took another line, let's say this line, then we started to calculate distance between this line and all the points as such. So yeah, so this line had this much distance. So similarly we went ahead and we found distance between these points, all the points, and each of the line, right? So while doing that, what we get is we find the best fit line, so that all the data points can be mapped, or the model can be mapped to all the data points in relatively good way, so as to get better predictions. So how are we quantifying, or how are we qualitatively saying that we are getting better, or means this line is better than the another line, or this line, or this line? So for that, what we are doing, as we just saw, is that we are calculating the distance between all the points and the line, right? So let's just say, go ahead and again say that y is equal to mx plus c, right? So what we are doing is that we are finding the distance between the line and this point. So let's just say this line is y predicted, right? Because we are going to get predictions from this line. So this line is for y predicted. So we are finding distance between y predicted and y, and we are using this as the quantifying or quantity that would actually tell us how good the line that we are currently fitting, means from which we are getting this y predicted, is. So what is this y predicted? So y predicted basically is mx plus c, because we are finding we are finding c using this line, and using all these m and c values for a new value of x, we are finding the y, right? So y predicted is mx plus c minus y. So we actually want to minimize this distance as much as possible between y predicted and y real, right? So for this, we define a loss function. Let's call this error or loss, because this line and the distance between y predicted and y actually represents the error that we are actually getting from that line right now. So yeah, so error is equal to mx plus c minus y, right? So since this value can be positive and negative alike, because sometimes the point x is below the line, sometimes the point the point y predicted or y real is below and above the line, right? So what we want to do is we want to find the square of this distance, so as to get a quantity that is in positive terms, because distance is always positive, right? Distance can be negative. So now we don't want this error to become a very large value. So what we'll do, for example, say there are x1 to ... and xn terms. So so x1 to xn, so we have similarly y1 to yn. So we have n number of values for our y. So let's just take an average of this error and make it 1 by n of mx plus c minus y square, right? So again, just to recap what we did, we found the distance, then we wanted to minimize the distance. So before minimizing it, we want to make it a quantifiable quantity. So what we did, since it's distance, we always wanted to be positive, so we took a square of it, and since we didn't want it to be become didn't want it to become a very large quantity, we took an average of that distance. So now this average is going to give us the total error or total difference between the line and the actual points overall. So now what we did by this formula is that we actually solved the problem which we faced when we wrote the formula for m. So what was m? y2 minus y1 divided by x2 minus x1, right? x1, my writing isn't good. Okay, so yeah, so this was for just these 2 points per se. So now we have we have a formula that now takes into account all the points on the graph, or all the points in the data set, right? So just to keep the formula not good, actually good isn't a word well enough for this, but since we are going to find the derivative, because if you have studied 11th and 12th mathematics properly, then you would know that to find the minima and or maxima of something, we actually plot and then find the derivative so as to find the minimum and maximum point. So we'll just discuss that again. So yeah, we'll discuss that first. So since this is a square here, so to get rid of this 2 term when we find the derivative, we'll just add a 2 here. So now we have an error function which looks something like this: 1 by 2m y predicted minus y square, or 1 by 2m mx plus c minus y whole square, right? So if right now this isn't making any sense, just stay with me, or I'm guessing it would make a little sense because we want to minimize the error. By now let's just say that we are trying to fit a line to the points in our data, and we want to make the line as better as possible. So for that we have a quantity known as error. So we want to minimize that error, because minimizing that error will get the line that we are trying to fit as close as possible to the data, right? So now for this error, if we want to minimize this error in terms of this value m and this value c, what we'll do is we'll find the derivative. So let's just say for now, it's a broad assumption, but it's feasible assumption that c is equal to 0. Now our equation is basically with 1 by 2m mx minus y. So now if I want to minimize this error in terms of m, what I will do is that I'll find the derivative of e with respect to m. So this becomes, so now the 2 is making actual sense because now the 2 will get cancelled. So yeah, now this is mx minus c, and then this gets multiplied. Since we are deriving with in terms of m, this becomes this, right? So this now is mx square minus y upon m. So this is the derivative. So now what we want to do, since the value isn't actually equal, value y predicted is not actually equal but almost equal to y, right? So what we want to do is we want to get these two values as close as possible. So for that we want to reduce the error, right? So what we'll do is we'll make our error, sorry, so for that what we'll do is we'll take a value of m and we'll update the value of m with a given value. This value is basically called as learning rate. So what this is, will get clear in a little while. So yeah, we'll take this, then we'll update the value with the derivative of the error with respect to m, right? Because we are trying to minimize the error with respect to m right now. So yeah, this is basically called as the update function, and the value gamma here is the learning rate. So learning rate is the speed at which our function actually learns. Means yeah, let's just take another moment and then we'll discuss how what learning rate actually is. So what did we just see? So we had an error which we wanted to minimize with respect to the value of m, right? So now let's just say we can plot these values on a graph where we have a m and where we have e. So now this we are getting into gradient descent, so please pay as much focus as you can. So now we have error and we have the value of m. So if we can map this value, and if you actually go ahead and try to map this value, since it was a squarish kind of thing, so this becomes something like this. So for a given value of m, if we have different values of m, and for that if we could experiment, for example, since e was is equal to 1 by 2m mx minus y square. So for we had x and we had y, we didn't know about m, right? So if we go ahead and experiment with different values of m, we'll see that this becomes a means this shaped curve. The reason for this is the square, right? So if you know, squares give you this kind of arc, or this kind of parabola. So so now for different values of m, for example, let's just say value of for different values of m, we are getting something like this. So when we plot, we get a line which is this line. So where do we want our error to be? As we said, we want our error to be as minimum as possible. So we want to find a value of m such that our error is as minimum as possible. So pictorially, right now we can see that it will lie somewhere here. So how do we get to that point? So again, let's go ahead and again write that equation, which was m is equal to m minus learning rate times derivative of error with respect to m, right? So now so let's say that we start with a value of m which gives you an error somewhere here. So now what we are doing is we are subtracting some value in such a way that we are moving somewhere downwards, right? So we are decreasing the value. Now as we go ahead and keep on changing or keep on updating the value of m, increasing or decreasing, whichever one it will be, because for this slope right here, this will be a negative value, this quantity will be negative, and hence this becomes m plus whatever dot value, right? So hence we'll move in this direction. Okay, so yeah, we'll move in this direction, and hence the overall direction is this way, right? And if we are somewhere here, if we are somewhere here, then this value is actually positive, and hence this becomes m minus of dot, and hence we'll move in this direction. So right, so what is this factor learning rate, right? So we want to move to the bottom, so why can't we just find a derivative that is good enough that directly takes us here? So that actually isn't possible. So what we do is we take this step, or we make the algorithm learn with this value of gamma, or this value learning rate. So it actually defines the speed at which we make the movement. So if I just go ahead and clear it up, so yeah. So as I was saying that we want to learn, but we want it to learn in a way that it moves to the bottom. So for example, if we are starting from here, and our if our learning rate is set to a certain value, then we might take little steps on this graph. So we might move one bit, then move another bit, then move this, then move here, and keep on moving such that we reach this point. So how does this value actually affect us? So for example, let's just say that we make this value a very large value, right? we set learning rate to a very large value. For example, let's just say we set it to 50. What will happen? So rather than taking these small steps, we'll take one big step. So what if this big step is in such a way that we move here? So after that, if we again try to, since we are on this point, if we again try to uh, find this value, then this value will become positive again, and hence will move in this direction. But since the value of uh, learning rate is very high, what will happen? We'll start moving upwards rather than going downwards, right? So what will happen? We were somewhere here, we moved in this direction, then again we moved outwards, and so on and so on. And this problem is known as overshooting, right? So what will happen if rather than making the value too large, we'll make the value too small? So for example, now let's this time say that we are somewhere here. So now when we keep on moving with a very small value of learning rate, for example 0.5 into 10 raised to power minus 5, let's just say this, since this is a very small value, if we are somewhere here and we start moving in this direction, we take small steps, keep on taking small steps, keep it on, keep it on, keep it on, keep it on, and as you can see that it's going to take a very large time, and it becomes computationally unfeasible uh, to actually move this slow, right? So what we want to do is we want to set this value of this value of gamma or learning rate in such a way that our update process gives us the optimal value in a feasible time and in a feasible manner, and it doesn't actually create more problem by overshooting or undershooting, right? So this value of gamma is actually determined by heuristic and is not something that we can actually find out. So we have to keep on trying different values and see which value actually fits our problem statement and our model the best, right? So yeah. So again, this is the cost function or the error function. We want to minimize it with respect to m, and we want to find the value of m in such a way that this value, we reach the bottom of this value, and this entire process of finding the minimum is known as gradient descent, right? So this was the very basic of gradient descent. Again, can be stochastic, probabilistic, and all these things, but we don't have too much worry about that. All we have to know is that gradient descent is how we are going to find the value of m, so that the value of m is such that we have a minimum error. So now let's go ahead and see how this actually will translate into code.